The Great Red Spot is one of Jupiter's most striking features. Scientists first observed the storm back in 1664 and have regularly tracked it since the mid-1800s. At its largest measured size, it could fit 3 Earths inside of it. But Jupiter is also home to an arguably more intriguing population of storms encircling each of its poles. We first learned about them in the mid-2010s, but to explain their existence, scientists had to go back to math from the 1800s, which described a completely unrelated phenomenon: floating magnets. Cyclones on Jupiter are basically the souped-up siblings of the ones on Earth. They follow similar trajectories, forming near the equator and diverging toward a pole. It's just that on Earth, the storms never actually make it to the poles. They run aground and lose energy, and the colder ocean waters also provide less fuel as they go. Meanwhile, gas giants like Jupiter have no surface to sap their energy, and their poles aren't that much colder than their equators, so these storms make it all the way up to the proverbial ends of the planet. In 2016, the Juno spacecraft observed a set of 6 cyclones at the South Pole and 9 in the north, ranging from 4 to 7,000 kilometers across. There's one storm about in the center, and the rest orbit around it at roughly equal distances to one another, and the systems have basically been stable since then. But in theory, the storms should have merged into one large storm at each pole, something reminiscent of the hexagonal cyclone on Saturn. Why they hadn't was a huge mystery. So one team hunted for an explanation, and for some unclear reason, they traveled back to the 1870s and an experiment with magnets. Way back in 1878, American physicist and professor Alfred Mayer published what was basically a classroom demonstration. It was about how molecules will naturally arrange themselves into certain shapes. In the demonstration, he magnetized needles and stuck each one in a cork floating on some water, with all the magnets' south poles pointing up. Then, he hung another magnet above the setup with its north pole pointing down. That way, the needles would be attracted toward a central point, but they couldn't get too close because their matching south poles would repel one another. This forced the magnets into different geometric arrangements depending on the number of needles. Really, it was just a big lesson in like repels like and opposites attract. The stuff about magnets you learned in elementary school just applied to molecules. And if you're looking for the connection, it had nothing to do with Jupiter. That part comes next. Not long after Mayer published his demo, the British physicist William Thomson, eventually dubbed Lord Kelvin, published some of the math behind it. He showed how the needles will force themselves into a certain state of equilibrium, balancing mutual repulsion against their common attraction. And the number of needles changed what those points of equilibrium were. Thomson published his findings not long afterward, and he also noted that Mayer's demo was a great analogy for column-shaped vortices orbiting a mutual center of gravity. Now that might sound completely unrelated to molecules to you, but at the time, Thomson hypothesized that atoms weren't particles, but vortices within a frictionless fluid called ether that permeated space. This is not true, but his math was legit. His proof showed that point-like vortices could be spaced out symmetrically along the circumference of a circle, remaining stable for up to 6 vortices. But once you tried to add a 7th, it became unstable. And future work would show that adding a sufficiently strong vortex in the middle could stabilize the system for as many vortices as you cared to fit around it. And this is, of course, where Jupiter finally comes back in. This 2020 team realized that, maybe the storms on Jupiter could be described with this old magnet math. They just had to convert magnetic attraction and repulsion into something else. And they did! The attraction became a cyclone's tendency to migrate toward the poles, which basically happens because of a net wind that forms inside the storms, pushing them either north or south. As for the magnetic repulsion, that became a special type of shielding on Jupiter, a ring of wind surrounding each storm that rotates in the opposite direction. And shockingly, this worked. The math applied to Jupiter too. Using computer modeling, the team used these equations to figure out how strong that shielding effect needed to be to keep the storms in the stable positions Juno was observing. The number itself isn't very important because it depends on the specific parameters of Jupiter's atmosphere and the storms themselves. Instead, the real point is that the math is once again legit. Equations from a century and a half ago can finally describe the layout of Jupiter's polar storms and why they haven't merged together yet. That said, there are of course still plenty of mysteries remaining, like we don't know how or where the cyclones first formed, we don't know why the number of storms has been so stable, and we don't know how this shielding managed to form around Jupiter's vortices, but not over on Saturn. So there's almost just as many questions as there were before, but eventually, knowing how the superstorms on other planets work will help scientists better understand the quirks of weather here on Earth. And really, this serves as a reminder that sometimes you don't need fancy new math or computers to solve new problems. Sometimes it's just a matter of looking for the right clues in the history books. Thanks for watching this episode of SciShow Space. If that aspect of Jupiter's weirdness wasn't enough for you, you might want to check out another one of our Jupiter episodes about how this giant planet is a total jerk, but also our friend.